real quick. Yeah, so now we have sound, but there seems to be an issue. You should see my screen. For some reason, it's not showing. It was showing before they played the banner, so let me try to plug it in again. That's weird. So, let's see. Now, better, right? So, trying to turn it off and on again sometimes helps. So, hello and welcome to that talk of mine. I'm really glad and happy to be here and still see someone around. You know, it's day 3 after a long conference packed with full of great content. A fantastic event is about to close, and there is still a good amount of people around, so thanks for joining. I want to share in this session, in the next 45 or so minutes, with you how we can benefit from a specific architectural pattern, a pattern that is, in my experience, one of the lesser known ones, probably one of the less popular ones, but I think it deserves a little bit more of attention because it's quite handy when we are facing the task of migrating existing software applications, hence also that talk. So the idea is that I'm showing and explaining to you how it works, also showing a demo step by step so that you have a good understanding what it means and how this pattern can actually help you with software migration projects. Let me start this by showing you a picture. What we see here on the screen is, to me, a pretty interesting phenomenon, memorable one as well, that we find in nature. It's a tree structure in the middle. It's probably a little bit hard to see at first sight because that tree in the middle itself is wrapped in some other species of plant. They are tropical plants and they are called Strangler figs. They got their name from the special growing behavior upon other trees. So these Strangler figs typically seed in the upper parts of their host trees, and then they primarily grow downward. Yes, it may sound a bit awkward, but that's what they do. So they grow from top to bottom until eventually they root in the soil around the tree itself. And so over longer periods of time, what they are capable to fully envelope that tree structure and literally smother their host trees, which means they are slowly but steadily killing the tree they originally seeded on. Why am I telling you all of that? Well, there is this architectural pattern that shares its name with these specific species of plant. It was originally just called the Strangler pattern, later renamed to Strangler fig pattern to take away the negative connotation of strangling something. And I want to show you how you can apply that. First, a few words about myself. My name is Hans-Peter Grahsl. I'm based in Graz, Austria. I'm working for Red Hat as a developer advocate, and I am an open source enthusiast basically for several years now. I have done most of my community contributions at the intersection of 2 different developer communities, namely the Apache Kafka and the MongoDB communities. But enough about me. Let's get down to business. And I think most of you know, or at least can imagine, that when we are facing the somewhat daunting task of migrating existing, probably aged applications, there are all sorts of challenges involved in doing that. Let's pretend for a moment that we have an old application. Most likely that application is monolithic in nature, because that's what we have done for decades. And let's also pretend that we evaluated carefully and we came to the conclusion that it makes sense that in order to modernize the application, or at least parts of that application, we would want to target either a service-based architecture, so domain services. There was a talk before lunch that explained the differences about that in detail, or also maybe even microservices. And so whenever we do that, whenever we try to build something new from something that existed before, there is, of course, more than just one way to accomplish that. What about the big rewrite, followed by a hard cutover? So literally something where we would pull the lever to swap from old to new after we re-implemented the whole thing. Well, I think you can imagine, or at least if you have heard or read about, maybe you have even taken part in a complex migration project yourself, chances are when you try to do that in a Big Bang migration style, that it didn't end well. In fact, history has shown us that Big Bang migrations are oftentimes doomed to failure. But then again, who am I to claim that, right? So there is a pretty famous quote from an even more famous industry giant that I'm pretty sure most of you, if not all of you, know quite well. And with that quote, Martin Fowler wants to remind us, in fact, he even wants to warn us, that if we try to do a Big Bang rewrite, the only thing we are certain of is, well, a Big Bang. So given that, what should we aim for instead? What could be a better, and I'm using better here in the sense of what could be a less risky way of migrating an existing application into something newer? And I think the overall migration goal here should be that we try to come up with a migration path that allows us to smoothly transition between the old version of a system and a newer variant. This also, I think, is in line with the inherently, say, gradual and evolutionary nature of software projects, right? We don't just a software system is something that we usually do in iterations, we do incremental steps, and we approach a larger goal by taking smaller steps. And I think migrating a system in that sense shouldn't be differently treated than writing a new system to begin with. And so, yeah, every migration takes time, and depending on the size and complexity of the original system that you want to migrate, these are definitely months, if not years. So the question is, what happens during that time? And the obvious answer is that we need to find a way that the old system can coexist with the parts that we already have migrated into some newer architecture. And again, the bottom line here is we try to achieve that goal because we want to avoid that risky Big Bang in the first place. So this is exactly where this Strangler fig pattern comes to the rescue. And on a very high level, how that pattern works is by repeatedly executing a process that consists of 3 phases. I'm going to quickly walk you through those phases, and later we are going to then, like I said, see and discuss on a concrete example how this can actually work. Phase number 1 is all about finding a starting point, right? You have that old application and you need to decide where do you start to extract things into separate services. Feel free to call them microservices if you prefer. Once we identify that, we try to take that piece of functionality, re-implement it, potentially even with a different tech stack that might be a better fit for what we want to achieve. Something that probably hasn't even existed when we originally wrote it. So that's also the chance in that sense to not only migrate the architecture, but maybe also try to introduce a new, better fitting tech stack. This assumes that the existing monolithic application has at least some sort of structure to it so that we can do an extraction in a reasonable manner. Then we enter phase number 2, and similar to how superheroes sometimes need to find a way to coexist, maybe even collaborate in order to survive, we need to do exactly the same thing. We need to come up with a way that while we are extracting and implementing that functionality, our new system can run in parallel to the old one, basically side by side, so that they can collaborate and provide us the overall feature set of the whole application at any given point in time. Eventually, we reach a point for one specific part of the application that we successfully extracted that we could take action and eliminate the same corresponding functionality from the original application. We don't necessarily have to really and literally remove it, but it's the safest way in order to make sure that the same functionality that is already externalized isn't going to be used any longer by the remaining parts of the old application. Let's take a concrete example, an example that is probably simple, but I think it's good enough to show all those steps that are involved in applying that pattern in this evolutionary way. So the way that this example works is as follows. We have, I took here a version of the Spring Pet Clinic app. You see from the version numbers that I purposefully took a rather old and aged version of the Spring Pet Clinic here. And again, this is on purpose. I know that there are brand new versions of it. There are even microservice solutions for the Spring Pet Clinic, if you have ever seen that. But I think to mimic that kind of vintage, or give it that vintage touch or nostalgic feeling, which we should have because we talk about migrating existing things, I did it that way. So that is a monolithic application, a pretty simple one. It has a couple of components, 4 of which are shown here. For those of you who have never seen it, very briefly, it's a fictional pet clinic that is basically given by that application. We have owner-related data, owners own pets. So we have a pets component that we can use to manage pets with. And then we have veterinarians and visits, so we can register visit dates for pets at veterinarians. And that's, in a nutshell, basically what that whole application does. And so we try to understand now what it takes to decide for one of those components and extract it into a separate service. The monolith here is backed by a relational database. In this case, it's a MySQL database. And the very first thing that we will do is we are going to introduce some sort of proxy mechanism. And initially that proxy will not do anything other than passing through all the requests as they are, so without taking any changes. All the read requests, all the write requests that are done from the web UI are handled by that proxy app, by the original monolithic application. And then we reach the point where we say, okay, now we say we want to extract the owner's functionality into a separate service. Of course, we need to find a way, how do we deal with the data? How do we deal with owner-related data that is also residing in that relational database here? And before concluding that example, I want to take a short detour, because that detour is necessary because I have to introduce you to a mechanism that is called change data capture, which is very, very handy in particular when we use it in the context of this Strangler fig pattern and software migrations. So who has heard about change data capture? I try to see some hands, at least some hands. Who tried it and used this mechanism before? Slightly fewer hands. Good. So very briefly, I want to give you the minimum viable information about change data capture based on a concrete implementation that we need to understand the rest of the example. So I've got to point you straight away to a pretty cool project, the Devoxx project, which is an open source change data capture platform. In a nutshell, what it allows us to do is we can take this project, more specifically some of the connectors that this project offers, and we can point those to a database or a data store in general, the support we're going to see quite soon. And we can then take a snapshot of all the existing data in the database and send that over some messaging infrastructure to any target system that we want to synchronize that data to. And after doing that initial snapshot, it allows us to continuously listen directly on all the changes that are happening in that database. So we can react to all the inserts, deletes, and updates that are happening in a database. Talking about databases, there is an ever-growing list of databases that this project supports. Currently, and I still think that this is up to date, it's 9 different databases. You see, most of them are relational databases, some are different in nature, and 3 of those, in particular Cloud Spanner, Vitesse, and also Cassandra, if I'm not mistaken, are in the so-called incubating state. The other 6 are generally available or production ready, so to speak. And so we can do that change data capture thing taking data out of those, and then continuously listen to any changes that are happening with all those databases that are on this slide using Devoxx. In my experience, most deployments of Devoxx are happening in the context of Apache Kafka and Kafka Connect. The way this works is that Kafka Connect in that case is a runtime. We use those Devoxx connectors. Within a Kafka Connect cluster, they will be started and they will do the job of bringing data changes from the particular database into corresponding Kafka topics. And once they are in Kafka, we can do whatever we want. We can access that data with all the means that we have available in order to interact with Kafka. Very often at the other end of that streaming data pipeline, if you want, we use different types of so-called sync connectors that allow us to send data from those topics into a target data store of our choice. There are other models, deployment models for Devoxx. So in case you don't do Kafka, that's fine. Most likely you might not want to introduce Kafka just because of doing change data capture, and that's perfectly fine. Even though Kafka is in many companies and places around the planet, it's not everywhere, so you might have reasons not to use it. So Devoxx can also be used in a different way. It basically two different modes that you can use it with. You can use it as a library, essentially putting it into an application, a Java application that you have, use this so-called embedded engine, which is a library, and do the change data capture thing similar to how it would otherwise work in the Kafka Connect context. Another option, if you don't want to write your own application to do that, there is an application already that exists that is called the Devoxx server, which gives us this shell application or this wrapper around the engine, and we can then configure it so that we can react to data changes in any of the data stores that it supports. And then in addition, other than with the Kafka use case, we can use different types of messaging infrastructure to send those data changes to. So there is, for instance, Amazon Kinesis, Parser, or Google PubSub. That's enough to know so that we can continue that example. So now that we know about that mechanism, we can apply this change data capture thing based on Devoxx and in this case Kafka. So we can introduce Kafka here, and we can make sure that we use one of the supported databases and the corresponding connector here, the Devoxx MySQL source connector. We instruct it, we just configure it to capture changes for the owner-related database table, and it will do that snapshot and then continuously send changes to a Kafka topic. From there, we then say, well, we ship those changes to a target database, the database that should be the one that should back our service that is yet to be written. So we found a way using change data capture to transfer the existing owner-related data and all the future changes to a separate database in a reliable and robust way. And then we can implement that service. We can implement that separate service that does provide this owner-related functionality. And also here, we can do that in multiple steps. We don't have to do that in one go. We can say we start by just implementing the read functionality of that service. So we serve basically owner-related data in a read-only model from that service. Later on, we can say, well, we also add the write functionality. And whenever we do that, we instruct the proxy, and that's why we introduced it in the beginning, to route the traffic accordingly. So owner-related reads are routed to the external service, or the other reads are still handled by the monolith. Owner-related writes, once we implemented the write functionality in the service, will be routed to the service then again, and all the other writes will be still served from the monolith. With that, what we then need to do is, of course, when you think about it, that we write and change owner-related data in the microservice side, we need to find a way to bring those changes back into the monolith, because, of course, chances are very high that those changes to the owner-related data are needed by other parts in the monolithic application. And so we need to set up basically another pipeline into the other direction. Again, we use, in this case, the Debezium source connector here for MongoDB, bringing document and changes out of MongoDB, and eventually use the JDBC sync connector to bring those changes back into the database that backs the monolith. With that, let me show that to you step by step in action, this first simple example. Let me go there, and I will share the repository later on. So what I've already done is I'm using, for that example, that is meant to be run in a Kubernetes context, I'm using here the OpenShift Developer Sandbox, which is an enterprise-ready Kubernetes offering by Red Hat. You can claim your own sandbox instance free of charge, and you can learn about container and Kubernetes technology for 30 days, and after those 30 days, you can renew that environment. There's literally no catch involved. You just need to register an account, no credit card or any other payment means, and you get a pretty nice Kubernetes, managed Kubernetes offering here to play with. So let's inspect the components here. We see a lot of things that we have seen on the illustration before. So we have here the pet clinic and the database. So basically in the lower left we see the monolith, and in the lower right we see this owner-related, this little service here with its own backing database, MongoDB. We have that proxy, which will route between those two worlds, functionality for the monolith and the other parts that have already been extracted. And we have Kafka and Kafka Connect up here as well. So let me open that proxy just to make sure that it works. This is the index page of the proxy. That looks good. So let me briefly show you the pet clinic if you have never seen that little tiny app. Quite simple. We can find the owners here. We can do a search. There are some owners in that database, about 10 owners. We also see already here some pets or the names of those pets listed. We can, of course, go into the details here. We have some veterinarian information and things like that. Okay, that's about it. And now the idea is that we do and execute those steps that we need, that we just discussed on the slides one by one. So the first thing we're going to do is, again, we have seen everything is routed to the monolith at that point. We're gonna, sorry, that's the right one. We're gonna register the source connector, and again, that is just a matter of configuring and instructing Kafka Connect to start capturing those changes. So basically, what this did here in my example is it created a job somewhere here. And this job instructs Kafka Connect here to run a Connect instance, and this instance will talk to that MySQL database, bring those changes up to Kafka here, and from there we're going to send it further then to our target data store. So let me first, again the wrong one, sorry about that. Let me first inspect. So this is where we inspect what ends up in the Kafka topic. So we're going to start another pod, and that pod should show me the data in Kafka. So this is a JSON notation here. So let me just take out one of these, because that's a little bit hard to look at like that. Bring it right here and just format it a bit nicely so that you see this is basically what we capture. This is one owner-related data record in that MySQL database table. We have a bunch of additional metadata information about the connector and the database itself, operation types and stuff like that. So drilling into all the details about that, how that whole change data capture payload is structured, is a little bit out of scope of that talk, but you can find all of this in the official documentation, of course. What matters is that we found a way to take that initial snapshot for all the owners in that MySQL database, send it to Kafka, and work from there. So the next step is we're gonna run another connector, and in this case it's a sync connector. It will pick that data from the Kafka topic and send it over to the MongoDB database. So at the end, we will have a collection there with documents that reflect the same data that we have just seen. So let's see if that data is already there by now. Again, it starts a pod, and then it does a query against the actual database. So we should see soon, hopefully. Let me check what it did. That the query is now running. So now we should see something here. Exactly, this is how the documents look like in the MongoDB collection. So we have these 10 owners here, but you get the idea. It can be thousands of records, but for the sake of a demo, I think it's easier to stick to a few. And now that we have the data there, we can do one thing. We are ready, and again, the microservice, the owner-related service, has already been implemented, of course, beforehand. It's already up and running. So we can instruct the proxy at that point that we also have the data there now, starting from now, to route these read requests to the microservice. Let me do that. And let's verify what happens. So the proxy is instructed to change its internal configuration. And what we are going to do then is, if a user is on that monolithic app and basically refreshes, we should see that we are routed to the microservice. In that case, it's written with Quarkus. It's just to show that we use a different stack for the microservice side. And we have that same view now, that read view served by that microservice. And again, all the heavy lifting related to making sure that the data reliably finds its way from our source database to our target database is delegated to that change data capture mechanism behind the scenes. Okay? At that point, remember I said we implement it in steps. So at that point, let's assume we don't have the write functionality for changing owner data in our microservice yet. So what happens is, if a user tries to change a record here, the proxy will still route me back to the to do the change on the monolith side, because we don't have the write functionality in the microservice yet. So here, if I'm going to say this is now called Bettina Davidson, and maybe we change the city to the beautiful city of Krakow, just to have some data change, and we update the owner. Remember, when we update the owner now, the owner will be updated in the Monolith's database. We see that now reflected here. We have that change here. And now behind the scenes, that change is captured by Debezium, sent to Kafka, and then taken from there and brought to the MongoDB database behind the scenes. So if we go over and re-execute that search, again, the read will be routed to the microservice. We should see that that change has indeed successfully been propagated over to the new microservice side. So now, we say we want to do also the writes somebody implemented, changing the data on the microservice side. So this means that the functionality was already there to begin with. So we can now instruct our proxy to also route write requests to that microservice and not send me back to the monolith any longer. Of course, I said on the illustration when I explained the example before, at that point we need to make sure that we remove the change data capture pipeline from the one direction and set up a change data capture pipeline into the other direction. So we're going to unregister those things, and again, all of this is configuration, so all of this can be nicely version controlled and be automated with a GitOps approach and all that kind of thing. So usually all of those things happen automatically. It's just that I show that to you step by step. That's why the script here always pauses. So we're going to delete those two connector instances because we don't need them anymore, and then we set up two others into the other direction. So when we write those changes in the microservices database so that they are sent back to the monolith, okay? And when we do that, at one point, we should see that the data flow is flowing into the opposite direction. So now when I go here, and when I take any other, let's say this one, you see that the writes are now also sticking to the to the microservice itself. And let's say this is called Carlos Garcia in, I don't know, Vienna. Just another change that we want to do. And if I update that, that update now was written in the microservice database, and now the change data capture mechanism brings it back to the monolith, because again, this change of owner-related data might be needed by other components that are still running in the monolith at that point. So here I can go to the monolith to quickly verify. I can force the detail view to be served in the monolith. Let me just go over there directly. And we see that this has been changed, so the monolith database has been updated accordingly as well. So that is a very simple way of how you could go and do that migration for this particular part of the app. With that, let me go back to the slide, because at that point, if you have followed carefully, you might have your, I'll have that slide once more towards the end, so I can skip it. If you want to scan that QR code, this brings you to the registration page for that free of charge managed Kubernetes offering called the OpenShift Developer Sandbox. So if you have followed closely, some of you might frown upon that approach of change data capture. What we actually did is we more or less took the exact same data model that we had in the monolith and exposed it to the outside world, because the change data capture mechanism directly took everything that we have in that database and didn't change it along the way. And this is something where you could say, are you crazy? Are you insane? How can we ever do that? Because this is one of the rules that you will probably learn when you read or study microservices in a little bit more detail, that you should not do that, because we are leaking our data or domain model to the outside world. Now, the first argument I would have is it really the outside world in that case? Because remember, our original idea was to migrate away from the monolith. So basically, it's not the outside world, it's just an intermediary world, and at one point, the other side will be removed eventually. That would be one argument. Now you could say, well, you are just like trying to argument. Still, I am not convinced. We want to have an anti-corruption layer. We don't want to expose the data model in a one-to-one fashion. And in fact, I would encourage you to take that really serious and not do that. Not even, I mean, maybe okay for the context of that example, but in general, don't do that. So what options do we have? And again, we can somehow find a way that we expose the data to the outside world in a different way. Nobody says it has to be in a one-to-one fashion. We can make changes to that payload as the data travels from A to B. And again, depending on how you actually implement that, you have different options. In the context of Kafka Connect, there is a very handy mechanism called single message transforms. And as the name implies, we can use it to transform the payload of single messages in flight. Meaning, as the change data capture mechanism reads data from MySQL, we can apply a source-side transformation and change that payload before it even makes its way into a Kafka topic. The nice thing about SMTs is also, maybe we don't want to apply them on the source side, you can also apply them on the sink side. Meaning, you can decide where the change of the payload structure in order to come up with a data model that is meant to be for the outside world, you can make those changes at either side. You can even say you do some changes before going into your messaging infrastructure and some changes afterwards. That's one way how to deal it. When I say what are concrete examples would be to rename certain fields, Remember, you don't necessarily want to expose the column names from your source database as part of the data change payload, so you can do simple things like renaming stuff. You can remove certain fields that you don't want to transfer at all from that table. You can redact information in terms of masking data. You could even say, well, I change data types, I need to do date-time conversions, things like that. Or you can even say, maybe there is some really sensitive data that I have to encrypt on the way out of the original system before it enters any messaging infrastructure. All of that are valid transformations. Second observation of that CDC pipeline is the following. You say, well, what we have seen now is still a one-to-one kind of replication of single database records from system A to system B. You might need something else. You might want to have some aggregate structure that you want to send to another service. And an aggregate structure means that you might have the need to probably bring data that was originally stored in separate tables together again. You want to pre-join them before you send them to your target system. And this is where stream processing comes into play. And again, you have many different options. Once the data is in Kafka, in my example, I'm using Kafka Streams because this is a quite reasonable choice in the context of this tech stack. But you have other options. Very handy thing is there are SQL abstractions, so you don't need to actually write code for that. Joining, for instance, owners and their pets together and have one aggregate that you want to send to the other side. There are SQL abstractions, Apache Flink, Apache Spark, other commercially backed SaaS solutions to do that as well in the cloud and stuff like that. So again, many implementation choices that you have, but at the end of the day, you need some sort of stream processor that allows you to bring data from different change event streams together and build aggregate structures. So, with that, and this is what we actually want to quickly look into as well, because if you have looked closely, I even mentioned it when I showed you the original view in the pet clinic, it showed the names of the pets in that owner listing. We don't have that in our service yet because we don't even have the pets-related data available in our microservice. So with that, let me go to the example once more, because I will do one thing. I will tear it down. I will tear that down and spin up the other one. So let me just delete everything here. I'm not deleting Kubernetes, I'm deleting all the manifests so that we have a clean environment and we can look into the enhanced example. Again, the enhanced example resides in a separate branch of that demo repository that I'm going to share with you so that you can try that out on your own afterwards. I'm just going to check out this case, the enhanced version. That's just another branch. And then I'm doing the same thing as before. I'm just running that demo script. And that demo script will now bring up the whole infrastructure again. And while this is happening, let me show to you the changes of that enhanced example, again, first on the illustration and then live. So what we see here is those two additions that I just referred to when we talked about some of the concerns that you may have about that change data capture mechanism. On the one hand, we see those T's, they stand for single message transform in that illustration here. And they will allow us to make changes to the payload in flight. That's the first part. And the second and more important part of that example is that we now want to mimic this original view from the pet clinic monolith also in the microservice. So we want to be able to show at least the names of the pets for these owners also when this owner service serves that read view. And for that, of course, we need to have a different change data capture pipeline that captures owners and also pets. We're going to end up with two separate topics in Kafka, and then we have that stream processor that is drawn here somewhere in the middle, over the Kafka logo that will kick in and take those two streams of data changes and bring those together. And it will build this aggregate structure of owners and their pets. And this again is a very good fit to send that aggregate as a single coherent document in my document database, which is MongoDB in that case. So let's take a look at how this basically works here. Let me go back to the example again. So we're going to register now a source connector for both tables, owners and pets. So the owners part is exactly the same as we had it before. So we should see, again, the owners being captured. I quit that because we had that. And then we see additionally now, when we tail the Kafka topic, we also see that we now have the pets data captured. And I just take out one such data record again so that you see roughly how that looks. It looks like that. So this is now one of the pets data set. And again, you see the owner ID that it refers to. So that's that foreign key relationship that we have in the original table. And this information is used by the stream processing app to join those change events together with the original owner events and to come up with that aggregate structure for us. So let me do that. Here we run now that Kafka Streams app. And that Kafka Streams app, written with Quarkus as well, it will be started right here. In addition, let's check that really quick. Yeah, the auto layout is a bit messy here, but this is the Kafka Streams joiner. And it talks to Kafka, listens to those two topics, and will join those, like I said, together, and then write the join result into a separate topic. And that separate topic is then what we capture again and transfer with a sync connector from Kafka to the MongoDB side, which is right here. And then the owner service can also show that data. So let's see if the stream processor has done something in the meantime. It should. So here we see, and again, I will just pick out one that it's a little bit easier to read. We see that what the stream processor gives us is this aggregate structure now that we have an owner and the two pets right here. So this is basically now that data set with those two pets that we have seen in the monolith right here. Let's see. This is exactly that data set here. You see those two, Lucky and Sly, and this is exactly that example here. And you see there is additional data. It's not just the name, it's a type, which animal that is, and we ignore that because, again, remember what we want to mimic is we only want to have the name for that owner service over there. And this will be done by using this sync side transformation in order to remove all those unnecessary things as the data travels out of Kafka towards the microservice. So let me stop that reading process here and set up the sync connector, which now transfers that aggregate structure to the MongoDB collection. And once that happened, we see this is again querying now the actual database. We see that MongoDB, we end up with those documents in exactly that way, that we now have the names available in the service, and that service, once we now change the route again, we instruct the proxy to, now that, that we are ready to serve those from the microservice to do that, and when I refresh here, I should be transferred, and I see now also the pet stuff right here with the pet names. And of course, when I make changes now to the pets, they are propagated, and they will be joined. The aggregate will be updated, and also the database update, and all of that should happen quite smoothly. So let me just check that here. I go to the. Actually, I want to go to the other view here of that view, that detail view that is right here. Should be that one. And if I edit that pet and say this is now called Leonardo instead of Leo and update that pet, That change of the paths will be captured, the stream processor will merge it, update the aggregate, and send it over to the other database. And if we find that now, we see that that change of paths has also been propagated. So also those aggregate structures can be nicely maintained and kept in consistence with consistently with the original source system. So the other way around, serving the right path now for that particular example is pretty much the same. So we would again change data capture pipeline such that it stops capturing owner-related data from the monolith side, because the owners then will be written just on the microservice side. So that's the same thing. So I think we don't need to show that part again. I showed the important changes in that enhanced example already. This is just concluding the thing, what I said. And then we can basically conclude that example so that at the end, now we can also, and let me do that, I think it still brings the JDBC connector in. And at the end, just to verify that, if we now on the microservice side say this is now called Jeff White, it should also reflect that again, similar to before. So if we go to Jeff White here and say again, force that read view on the monolith side. Let's pet clinic. The route is just HTTP. So yeah, we see Jeff White here. So that's concludes basically that enhanced version. Let me quickly go back to the slides once more. We are about to wrap up. There are something like 4 minutes left, which means we are doing good in time. So with that, I hope I could show you how convenient it is to, when we leverage two things, when we try to follow this inherently evolutionary nature of changing things. It doesn't really matter if we build something new. It doesn't really matter if we migrate something existing. We should do it in an incremental fashion, in an iterative approach. We want to take those baby steps instead of trying to take this big bang rewrite and do one big leap to reach our target of rewriting a large and complex application. Of course, an application such as this you can easily implement in a different architecture, probably in a matter of hours or let's say days at most. But something that is more real world will, like I said, take you months, if not years to do. And you have that nice temporary coexistence. What's also important to keep in mind is if you do it that way, you can pause, you can stop your migration efforts at any given point in time without losing all the money that you spent until that point. And again, maybe the original goal was not even to completely get rid of the monolith. Maybe you have just had the task to extract those parts of the functionality in the monolith that gave you trouble, those parts that really were painful, those parts for which you need some characteristics that you couldn't fulfill in the monolithic architecture, and that's perfectly fine as well. So maybe you end up with that hybrid architecture of a good amount of functionality still residing and remaining in the monolith for years to come, and just externalize those parts where you absolutely need to take action. That's a totally viable approach as well. Ideally, and I think you can imagine that if you take enough care, you can even reverse some of those extraction steps again, similar to how. So basically, you would do it in the opposite direction, right? Maybe you have had too much granularity for some of your microservices. You want to merge them again. Also, that is something that you can do in a similar fashion. The Strangler fig pattern was even, when it was basically described, it was first applied for migrating monoliths to newer monoliths. So at later stages in time, that pattern was used for migrating between different architectures as well. And so again, I hope I could make the case with that presentation that this pattern is useful. It can significantly reduce the migration risk. So in case you need to have challenging migration projects, give it a thought, and maybe it's a good option for you to do that. If you liked what you heard, I would love to stay in touch. I think it's easiest to do that on Twitter. I'm quite active there. If you want to try out that whole example, everything is in this repository here. The link is there, the QR code is there. So all those Kubernetes manifests that spin up all the pods and containers behind the scenes, everything is pre-configured. So also the script that I used for the demo is there, so you can walk through that step by step anytime. And all you need to bring is the Kubernetes environment, and again, you can use the OpenShift Developer Sandbox for free, just as I did here in that presentation. We have about 7 seconds left. This is the last slide, just a collection of useful resources, again, with the explicit links. That's it. Thank you so much for sticking around. That's all I've got. I hope it was interesting and useful. Thanks for being here.